Welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording, the electronics reporter. Autonomous vehicles continuously make headline news, and not always for good reasons. The autonomy afforded in Tesla vehicles has often been overestimated by drivers, and even placing a human as a backup in prototype vehicles has not avoided collisions. Currently, the only way for most of us to experience real driverless cars requires a trip to San Francisco, California or Phoenix, Arizona, and then it's only a Waymo's ride-hailing service, not a car you can purchase and own. So did we underestimate the challenge of autonomous driving, and are today's vehicles even ready to support such capability? To find out more, my panel of experts in this episode are Giancarlo Cutrignelli of Eurotech and Peter Gliwa of Gliwa Embedded Systems. Welcome to the show, everyone. I'm going to start with Giancarlo. Bring you up here on the screen.
Hi, Stuart.
Hi. Good to see you. Firstly, can you tell us briefly about yourself and your role at Eurotech?
Absolutely. Thank you, Stuart. So my name is Giancarlo Cutrignelli. I'm Director of Product Management at Eurotech, which is a leading company in providing ADAS solutions, hardware and software solutions.
Super. Thanks very much. And let's pull in Peter quickly as well. Welcome to the show, Peter. What keeps you busy at Gliwa?
A number of things, I would say. So we've been looking for the past 20 years mainly into the topic of embedded software timing. And in this context, we provide tools and services. Yes, so that's what we're dealing with.
Smashing. Well, thanks very much for that, and we'll be back to talk to you very shortly. Now, this episode is sponsored by Espressif, creator of the ESP32C3. This single-core Wi-Fi and Bluetooth 5 LE microcontroller SoC is based on the open-source RISC-V architecture. It strikes the right balance of power, I/O capabilities and security, thus offering the optimal cost-effective solution for connected devices. For powerful AI acceleration, you should consider the ESP32S3. With the same wireless features, it's designed for AIoT applications thanks to its powerful AI acceleration and reliable security features. It also has support for vector instructions in the MCU, speeding up neural network computing and signal processing. For more information, check out the links with this video on Elektor TV Industries channel. So there we have it. What I'd like to do, of course, as well is make sure that you have the opportunity to get your comments and questions in during the show, because in my role as a deep tech journalist, I get plenty of chances to talk to people about autonomous vehicles and how they're going to be implemented. But what worries me are your concerns. What are you struggling in with your designs? So regardless of where you're watching, post your questions and comments during the show using the chat function either on YouTube or LinkedIn, or send us a tweet via Twitter using the hashtag ElectorEI, and we'll do our best to get answers or guide you to resources that might help as quickly as we can throughout the show. So let's bring back Giancarlo. Hi again, there we are.
Hey again.
So what I wanted to start with was that as I said in the introduction there, we've all heard, I think, a lot about autonomous cars, and engineers, we probably have a feeling that we know a little bit more about the details of how they're developed. But how is the industry sort of collecting all the necessary data and then processing it and training those algorithms that they keep talking about, which are going to make these cars safe on the road?
That's a good first question, Stuart. And let me say first that the industry, I think, has underestimated the challenges and the effort, right, to get to autonomous driving. And I think that this is clear to most of us now. Nevertheless, if you look at the numbers, the market predictions, autonomous driving is still expected to be $220 billion in 2030, right? So that means that the expectations in this industry are still high, then the demand from the customers, the end users, is still very high. So I think that the industry has reached a point of no return in developing and committed to deliver on this promise, right? To your question, right? So how those data are collected. So the good thing is that the right technology is in place. So Eurotech is providing this right technology to process this data, collect and process this data. there are different approaches to autonomous driving, right? So one of the traditional approaches is to use the so-called V model. V model is a system engineering way of proceeding. So you start with synthetic models, right? Developing your system. So you validate this with simulated data. But then there is a point where you want to validate and improve and optimize this data in real life. And the way you do that, and probably this slide will help me showing this to the public.
Yeah.
Right. So the way you do that is essentially replacing simulated data with more realistic data. So you start with a model, then you move into software model simulations, and then you start having hardware into the loop that is verifying in real time what you actually have designed. The ultimate goal, and that's especially when Eurotech comes into the play, is where actually you have a vehicle in the loop. And this means that your models are validated and optimized in real time in real vehicles and test drives, right? So why is this so critical and challenging? Because processing this huge amount of data, we are talking about even 40 cameras mounted on a car or 4 to 5 radars, right? So we are talking about a huge amount of data to be collected in real time and stored. Well, the challenge is that you want to pack as much processing, communication, and storage capabilities into the trunk of a test car.
So obviously this draws to something that we've talked about on this show before with the V model. That's the classic way that any automotive system, any sort of ECU is developed. So where obviously then we're applying that to the autonomous driving and the algorithm creation process. So in this process, when we're doing that work inside the vehicle, this vehicle in the loop part of the process, what are the sort of day-to-day challenges that the team are having with driving the car and collecting data and evaluating it and improving the training?
Right, absolutely. So, well, the teams are normally faced with the need of handling this huge amount of data, which means acquiring them, then processing them and storing and moving them maybe in lab servers for further processing, right? So that's it. You need to imagine that this is an iterative process. It doesn't happen once, it happens over and over again for further optimization. What are the challenges? Squeezing all this processing capability inside the trunk is already the first step, right? So you have a small space. Small space means that you have heat dissipation issues, that you have power limitations, and then you have a very, let's say, rough environment to deal with. It's a typical automotive environment, paved or unpaved roads, vibrations, shocks, and so on. Well, how do you solve this? Well, first of all, there is a cooling approach, right? A type of solution that you need to bring onto the table. And in Eurotech, we have solutions that go from active air, like a fan, a traditional fan, to a hybrid liquid and air solution to a full liquid solution. This allows not only to shrink the space and the capabilities into a smaller form factor, but if you think about liquid cooling, this is also bringing a zero noise environment, which is, you can imagine driving 7 hours a test drive. This could be actually a real challenge. The second problem.
So I was just going to ask a quick question there. With those test drives, is that sort of like a 7 hours done by a single person, or do several different people go out in the vehicle during that time, or is it a team effort?
I guess that depends on the setup of the individual OEM, or how the labs are organized. But it's not impossible to think that you have test drives going there for a full working day around, because you want to collect as many extreme situations as possible and validate your model against it. Yeah. But in extreme cases, yes, you have a full working day. You have 6, 7, 8 hours of time to collect as many data as possible in a remote location. Now, let's do just a quick math, right? So we are talking about 40 cameras, 4 or 6 radars, and different other sensors. If with the technology of today, we are talking about 40 gigabit per second type of data that need to be processed and stored. Do a simple math, you can fill a 128 terabyte hard drive in 7 hours, right? So just to give you a bit of a feeling, and how fast and how large this type of storage needs to be. So to your question, what are the challenges? The development team, after 7 hours of drive, need to take this huge amount of data and move it to a lab server for further processing. Transfer data is challenging. It takes time, right? So we have solutions to physically unlock this storage and move it and transfer it one-to-one to lab servers. And this is actually saving time, reusing hardware, and improving reliability of the overall solution, right?
Yeah. So one of the terms that often comes up in these discussions are high performance computing. And from sort of my background and experience, when we talk about HPC, high performance computing, we're typically talking about large servers in universities and research establishments, which are incredibly powerful for predicting the weather, for example, and other types of events like that. What for you is a high performance computer, and how is it, how does it differentiate from the other types of computing platforms that you see in an automobile today?
That's an interesting question, right? So it comes to the definition, and HPC, so high performance computers, is quite a wide range, encompasses a wide range of solutions. If we look at the ADAS or automotive type of applications, what I see, especially if we are talking about neural network models and so on, I would stress the fact that they are in the edge. Right, edge means at the ultimate point of use, and that's why in these cases we prefer the term HPEC, HPEC. So high performance edge computers, to highlight the fact that they are really where the data are collected and acquired, and this highlights the cooling and the ruggedization issues that this brings to the table. So we are not working in a lab environment, in a secure artificially cooled environment. We need to deal with these problems ourselves, so internally to our device. So HPC, I think, it defines better what we offer and what is required in the ADAS market.
Now, I'm based in Germany, and often when we're driving around the city, there's a few well-known automotive manufacturers here, and plenty more that like to test the roads around us as well. We see the test vehicles, and they're kitted out with cameras and LiDAR and radar and other sensors. You already mentioned sort of like the quantities of data that those sensors are gathering, but what sort of interfaces are they relying upon in the vehicle, and what does an HPC or HPEC require in terms of functionality and interfaces to collect and gather all that data?
Right. So as you can imagine, all those sensors have high speed, right? So especially cameras, vision devices need to have a very large bandwidth. So physical interfaces are pretty standard. What is important in that case is that the speed of the overall system can keep up with the feed of data feed that this sensors is providing, right? So a typical example, and I give you an example from a real project that we followed. An OEM has been developing a solution where 128 terabytes of storage capacity, so an AI server, was coupled with AI, so GPU powered HPCs, and in that case we could allow 800 teraflops of processing capability, which can be easily doubled to 1.6 petaflops. So this is a huge processing capability, and to make all these things work together, you need to have 100 gigabit network switches. And I think that this is one of the keys, and is answering your question. You need to have also high networking capability to allow all the systems to work all together in real time.
Yeah. And in those sort of test vehicles, are we talking about standard Ethernet, or are they also using automotive Ethernet, which obviously is designed specifically for real-time applications?
I guess most of the demand when it comes to ADAS development, let's say, tries to pick what the industry can best supply, right? So the automotive development versus the commercial, right? So the mass development has different requirements, and I think the test engineers in the ADAS world want to have the best they can offer, and the automotive requirements are maybe more on the ruggedization aspect, right? So because they want to have expensive equipment to survive long test drives, rather than complying to the interfaces standards that automotive is mandated. As long as the system works and it can connect to test sensors, I think they are more than happy. This means availability, a capability to source the different components and so on. So it's performance first.
So Eurotech, I was looking on the website, you've got a range of edge computing technology specifically to support those developing these autonomous vehicles. Maybe you could provide us with a little overview of what the options are and where they're actually then used.
Absolutely. So you can, yes, you can. I can get the help of a slide here. So there is quite a large family, and we are able to cover for the others development all the different stages of data acquisition and processing, data logging, and in-vehicle AI inference. Right. For this type of applications, you need to favor one aspect rather than the other in the capabilities. For example, if you look at the central solutions there, this type of platform can become an AI server where the number of GPUs is maximized. You can think we can reach up to 4 NVIDIA A30 GPUs in this type of systems, right? And then this is an AI server. When it comes to a data logger, we can provide this type of solutions with, at the moment, 384 terabytes of storage capability between internal and removable type of storage, right? So flexibility, I think, is the right keyword here. We have different solutions which excel in the storage capability, in the AI processing capability, if you want, and then you see left and right, we have also top class type of a cooling capability with fully liquid cooling, or top ruggedization when they are automotive certified. Think about the LV 124-1 type of standard or EMARC. Some of our solutions come also with top automotive certification.
Now, one of the terms you've mentioned a couple of times, which is specific to sort of deep learning applications and the algorithm development, is this term inferencing. Could you just explain what that means in terms of the algorithm development process?
Absolutely. So neural networks normally are, let's say, at the beginning, stupid models, right? Stupid neurons which are connected to each other. And when they are, let's say, trained on sample situations, think about a road with people, with other cars, pedestrians, and signs, it starts to get trained, right? So it gets trained to give a certain answer to a certain stimulus. Inference is the moment where this neural network is asked to provide a guess or an interpretation to a certain situation, right? So inference is what a camera would do in normal operation. Okay, so if there is a pedestrian in front of you, it will just command to stop the car, or if there is a sign to reduce the speed, then it will command to reduce the speed. So inference is fundamentally the activity that the neural network is doing in normal operation.
So, and then just to clarify, the computing platforms we're talking about here, these are not driving these cars during the development process. They're simply testing the ability of the algorithms in a real environment, but without controlling the car.
That's correct. So during test drives, essentially the models developed offline, right? So get optimized and improved over time, and the activity, or let's say the interpretation or the actions triggered by the let's say the test equipment, is validated against what a human would do, and that's exactly how these models get improved, right? So they improve their association to the right action with the right stimuli outside. That's correct.
Now, most of us in our engineering community and our viewers as well will have at some point sat down and configured their own PC to meet precisely their expectations and needs. Is that also the case with these sort of platforms? Do I have sort of playroom to tune the processor, the GPU and the storage? And are you using hard drives on these systems, or are they solid state storage?
Absolutely. So you mentioned a very important thing. Configurability is key to this type of application. So because it's development where our customers and we with them are learning day by day what the requirements are, right? So configurability is essential, and also the possibility to upgrade the systems is essential. So back to the slide I was using before, you see that these systems have the capability to upgrade their storage capability and to upgrade their AI processing capability. So, for example, as I mentioned before, a real customer that we are following started with 800 teraflops of capability, but the same system can be upgraded to 1.6 petaflops. And the same holds here. You could start with 1 or 2 NVIDIA GPUs and then upgrade them when you need more processing capability, or the number of sensors you're connecting to it increases, right? The same holds for the storage capability. You're right, this is solid state drives. They are mounted internally, and they can also be extended with this removable storage, which we call quick tray, which are fundamentally some, let's say, ruggedized systems that allow the quick transfer of those drives from the car to lab service and vice versa.
Super. Well, thanks for that introduction to the world of algorithm development for autonomous systems. We're going to move on now briefly. So if you stay with us, we'll come back to looking a little bit more. I have a couple of questions I've written down because I'd like to know a little bit more about the cooling aspect of these systems. So we'll come to that later. So thanks very much for now, Giancarlo, and we'll move on to the next part of the show. So now we have our competition giveaway, which is something that we put in place for all of our loyal viewers every show. So firstly, before we start with that, I'd like to say congratulations to last episode's winner, who was Sion. Your Fortissimo 100 amplifier is on its way. Of course, you need to build it yourself, but that's all part of the fun. And to extend our thanks to you as a loyal Engineering Insights viewer, this episode I have a TO1104 Micseg oscilloscope up for grabs. This has 4 channels offering 100 MHz bandwidth. It provides 28 megapoints of memory depth and a capture rate of 80,000 waveforms per second. This tool incorporates an 8-inch colour TFT, and it runs for up to 5 hours on its lithium-ion battery. For your chance to win, simply visit the link shown below and enter the keyword deep learning. That's the keyword deep learning with your entry. So congratulations to our winner last episode, and maybe it will be you next time. Good luck. Now I'm going to come over to Peter. Hello, Peter.
Hi.
I can just move that oscilloscope out of the way of your face.
Well, I was actually tempted to right away punch in the what to say, because that would be a nice gadget, yeah.
Yeah, exactly. No problem. Give it a go. You might be lucky. Just to remind our viewers who are watching live, you can add your own comments and questions if you're on YouTube and LinkedIn. There's a comments and questions area where you can communicate with us. And if you're using Twitter, just use the hashtag ElectorEI, and we'll pick up your tweets there and add them into our question and answer session, which comes towards the end of the show. So thank you, Peter, for taking the time to join us. On this show, we've spoken about the importance of timing within the context of automotive applications in the past. I thought it'd be nice just to go back to the beginning of your founding of the company, because this is, what you do. What was the sort of first time that this timing issue became apparent to you, and how did it then lead on to you saying, yeah, I need to form this company, Gliwa?
Actually, I have been asked by one of our customers, BMW at that time, when I was still working at ECUs as a product manager and software developer for the HPEC operating system. And at that time, more and more projects actually got in touch with us as an OS vendor, so ECUs as an OS vendor, asking for help because they observed weird behavior of their software and didn't really know what was going on. And more and more often it turned out just to be timing problems. They're not obvious timing problems very often. So they're really hidden. As I said, there's some weird stuff's going on, or even sporadic system crashes and these kind of, sort of things. And very soon it became obvious I need to have some way of visualizing what's going on. Because if you're new to a project and you're trying to find a problem that others, maybe a task force, has been working on for even weeks, and they know their project, and you have to have the possibility to get a quick insight into what's going on. So reviewing source code doesn't help. You need a different, let's say, flight level.
Yeah.
And when it comes to timing, the flight level of execution of tasks and interrupts is exactly what you need. So this kind of flight level to look down at what's going on timing wise. And in many of the projects, then you will observe that, you've got sporadic high load scenarios, for example, and sometimes they occur very rarely. So you need to be able to trigger on these kind of situations. And I'd like to describe a situation that we had really many times. So the image of the integrator, the software integrator, getting pale in the face and falling back into his chair with the mouth open and saying, "Oh my God, if this is what's going on, well, it cannot work." So having the visualization of what's going on, the trace, actually, the operating system trace of the execution of tasks and interrupts. This is what caused this kind of pale face several times, actually.
Now, you made an interesting sort of a statement in there, which I think those who aren't involved in the automotive industry may have sort of glossed over. But can you just describe what happens when these sort of sporadic failures are found? Because they're right at the end of the development process. And from what I've heard, at least, you mean, like you say, you get a task force comes together. What's that like? And sort of what are the expenses involved for the entire development team, all of the players, in sort of resolving these essentially tiny issues which are stopping your next car rolling onto the streets?
So these were a few questions. Let me start with the last one. There I'm referring to a project actually 2 weeks ago. It popped up. So it's a car maker, and they are facing resource problems with their software for actually several ECUs, and the value that they stated now. So what they're thinking about is really upgrading the processor. So in a advanced state of the project now, they're running into trouble, and they are thinking about using a more powerful processor. And the estimated costs for that is 160 million euros. So we're not talking about peanuts. We're talking about really a lot of money. At least for me, that's a lot of money. And if you can avoid switching to that processor because you optimize your software, you make it more efficient, you make it run faster, you spread the load on the time axis. And I mean, there are a number of things that you can actually do, and which we have done in the past. So in my book, for example, I refer to one case where we saved around about 12 million euros with exactly this approach of optimizing the existing software and avoiding the switch to a new generation altogether. So there's a lot of potential for saving a lot of money involved. But to come to the other aspect you mentioned, yes, sometimes this becomes obvious in a late phase of the project. Not always. Sometimes it's even let's say a few months or maybe a year into the project, they estimate that the resources will become a problem, looking at the timeline, looking at their plan of which functionality is yet to be integrated. But very often it is really this task force mode where maybe they have been ignoring some of the problems for some time, and at some point you just cannot ignore the problems, because you won't go into production with these kind of things. And talking about rare problems, we had one quite dramatic one with a German OEM a few years back, where really top-level management was involved, and the SOP was in danger. Wow. And they had a task force working on the problem for several months, and they were really, you could see that they have been working with this quite a lot. There was a whole presentation they ran me through when they put me in, explaining what was going on, and they were so familiar with these slides and explaining the problem to someone, and that actually occurred 5 times in 2 years. The software bug that they could observe it.
Yeah, 5 times in. Yeah, amazing. So this brings me to another point. So as we know, sort of having attached to the industry, automotive software development side of things, you more than me, to be honest. There's so much testing that goes on. Everything is tested. It's tested in static analysis. It's tested in the system itself. There's this huge, expensive hills, sort of versions of the electrical part of the car that are built. Why are software issues still making it all the way into a production vehicle?
Very good question. And I feel the answer to that is probably multidimensional. So there are several effects. One of them being that the whole timing maybe has been not underestimated, but not being addressed as much as it should. So we talked about the V cycle already. And maybe you can show the slides I presented. If you start with, let's say, slide 8. Yes, if you fast forward to slide 8. Yeah, that's the V model as we know it. And we've seen it previously already in Giancarlo's presentation. And so it's very well known and widely used. And whenever people use it, mostly they are thinking of the functional aspects of their software. And what I would like to encourage everybody to do is to also address the timing topic. So if you switch to the next slide, you don't need to reinvent the wheel or anything. All you need to do is really apply the existing processes and development cycles, steps, and everything, also to the aspects of timing. So you can come up with a certain timing design, really think about in an early stage, what are the timing requirements, for example, and then take this timing aspect into all phases of your development. If you do that, already it's the risk of running into really big timing problems in the late phase of the project is reduced to really a small fraction of what it previously was. So don't just let timing happen, but really address it in a, let's say, organized way. And you mentioned static analysis and model-based analysis. So there are a number of timing analysis methodologies. And now the question is, which are the right ones to pick?
That was going to be my next question. Yeah, exactly.
I'm afraid the answer again is not simple, and it probably will vary if you ask others. So we provide tracing-based software instrumentation, trace-based solutions. So obviously, I'm a great fan of that. If you go to, let's say, the avionics industry, they require model-based approaches quite a lot. And some of these find their ways into automotive software development as well. And it depends actually what you want to achieve. But to give you a quick answer in a nutshell, so my recommendation for something that is has proved to be a very, very good approach is in an early phase, use scheduling simulation to get a very clear picture and idea of what you want to do, and then use tracing-based approaches, measurement approaches. So look at the real world, use debuggers or use our solutions to make sure that what you planned earlier through simulation is actually, well, happening in the real thing. So make sure to have this look at the real world, because in the end, we're going to build real cars and not virtual cars. So you have to switch to the real world at some point.
So could you maybe also go into a little bit more detail about the instrumentation approach? My understanding from what I've been reading is that the sort of one of the core instrumentation tools or solutions that you provide, that is actually integrated into the software during the development process and continues to live there and could be used by the vehicle manufacturer like a BMW or a Renault once the car's actually on the road.
Yes. So maybe if you switch to one of the slides that gives a nice overview, I think slide 4. So that's the book.
That's the other one.
Yeah. So yes, exactly. So you have a really let's say our product on one page. So the basis for this is software-based instrumentation. So we add a little bit of code to the existing software to gain information about the timing aspects of the existing software. So we put in some hooks. We hook onto the operating system and capture events which are relevant for timing. And the code that actually does this is certified according to ISO 26262 ASIL D. And that allows us to optionally leave this code inside the software, even if you go to production, and not only observe the timing of the software, but really supervise. So you can specify certain limits. For example, you can transform timing requirements into these limit checkers, into these constraints of supervisions. And if in the real system then they fire, well, you can switch to some safe state, for example, or at least make an error buffer entry, DTC entry, so that you know that you still got a problem. But this can actually take place in the real production version of the software. And the first year where we had this certification was back in 2016. So it's been there for quite a while, and there are millions of steerings and braking systems. So really the ASIL D, the safety relevant stuff out there on the road using T1 as part of their safety concept.
Now, I think in the world of business and consumer PCs and also smartphones, we moved to multi-core processors a long time ago. But the automotive industry, I think, was a little bit slower as it is. It's a bit more conservative and wants to make sure that the safety element is there, and also the reliability to sort of protect brands and brand names. When automotive manufacturers take an existing ECU, say for a steering or braking application, and then move to multi-core, does that immediately sort of resolve a lot of problems for them, or does it sort of create as many problems as it solves?
If we're talking about the number of problems, I would say it's not a good deal, because they gain many problems. Yes, so according to my experience, really the effort for switching from single core to multi-core really has been underestimated in each and every project. And there are several reasons for that. So you mentioned that we are using processors that actually come from other domains. Like, I mean, here everybody's got a smartphone or the laptop we're using. They're not single core; they're all multi-core. So actually, you should say that multi-core is the standard, not single core. So why is automotive software development struggling so much with multi-core if multi-core is actually the standard? The answer to that is quite simple, actually. It's a different kind of parallelism. So when we look at a smartphone, at a laptop, Windows software, Linux software, whatever, what you are looking at is application parallelism. So you've got different applications which run in parallel. And what you're doing is you're developing an application for these kind of systems. You don't even know about other applications. You don't even know on how many cores this will be running, for example, right? So that's a different story, really. When we look at automotive software, the idea that many software developers had and still have is, okay, I've got a certain functionality, which are now spread onto different cores, and I can just multiply the efficiency more or less with the number of cores I have. That's the initial idea behind this, and then they find that this doesn't really work. The reason being that we're looking at functional parallelism. So you're trying to run the same functionality in parallel, and therefore you need to really, in most cases, recode your functionality.
Yeah.
Again, I mean, I've mentioned the book a few times. Let me just point to that. I've got the hard copy here. So there, I'm giving an example, and I'm picking the very simple bubble sort algorithm, which everybody really knows, and which is straightforward and simple. Now think about porting that to multi-core. Right, I need to split up my data, and then I have different chunks which get sorted, and I need to merge that somehow. So the same functionality on multi-core requires a completely new implementation. And this is what many projects were not really ready for, which an aspect they haven't really thought about. Other aspects are ensuring data consistency, for example. So I just recently gave a talk on that. So in let's say in the single core world, especially in the very old single core world, to achieve data consistency, you protected some code blocks with disable, enable interrupts. Okay, right. And a few years later, with the introduction of OSEC, AUTOSAR, this already these turned into function calls, which are more expensive. Then we introduced safe operating systems where you do need to perform checks whether it's allowed to disable the interrupts in that context. And already we're talking about efficiency factor compared to the initial interrupt suspension of like 20 or 30. And with multi-core, we use spin locks, and then even cores can block other cores. So the costs of that explode. And if you now have a project that ports single core code to multi-core and simply replaces disable, enable interrupts with get and release spin locks, which is what several people did in the past, they're not having great experience with that in the end, because they find that their processes, they wasting time, the different cores waiting for each others, and spending a lot of time in the basic software.
Yeah. So one last question before we bring Giancarlo back again. Through what you've described, these problems that people are having, if the team is sitting there and listening to you saying, well, I think you have a timing problem because there's not enough processor cycles to execute everything here, and obviously something's going wrong, and then you propose adding some software, some instrumentation software, I assume there's a certain amount of reluctance from the team to adding more software to something that's already on soft ground. What impact does running T1 have on the CPU and system load?
Yeah, so it's certainly less than 1% per core, CPU load per core. So typically we're in the range of 0.2 to 0.4%. So yes, you're absolutely right. We do add more software to the existing software. But this used to be a topic like 10 years ago, maybe. In the meantime, this is not a big topic. Everybody understood that you need to be able to look into it, and what you gain from that is so much that these 0.2 to 0.4% per core, they're happy to spend that.
Great. Well, thanks very much for those insights. What we're going to do now is bring Giancarlo back into the discussion. there we go. Good to see you. Still there.
You too, yes.
Super. So just to remind everybody, if you want to post any questions and ask our experts about some of the challenges that we face around autonomous driving and automotive architectures, feel free to pop them into the chat in YouTube and LinkedIn, or drop us a tweet with the hashtag ElectorEI, and we'll add them into the mix as we go along. So one of the questions that I wanted to start with was actually to go to Giancarlo and just ask, who is it that is currently developing these algorithms for the autonomous vehicles? Is it the big players, the OEMs, or is it the tier, as we call them, suppliers who supply those sort of things? Or are we also seeing lots of new players who are specialized in deep learning and algorithms, and it's them that's sort of doing the bulk of the development?
Well, I'm not an expert of the whole ecosystem, right? So it's difficult to make a short description of it. To my knowledge, this goes at different levels. So you have OEMs deeply involved in investing huge amount of resources into the development. You have also tier ones, so the likes of Bosch, just to to connect to Peter background. And you have also a number of small, medium companies which have started there to exist with ADAS solutions in mind, right? So what you see in the last couple of years is a consolidation of this market, right? And this connects to what the beginning of our discussion. So there was a huge hype about ADAS, and there was a huge, let's say, growth of startups and initiatives and activities, thinking now is the moment to win my place and to grow because of the other solutions I can provide. In reality, the resources to invest for this type of applications are huge, and fewer and fewer companies can afford to keep up with them. That's why I believe there is a significant consolidation in this market. So the big players are surviving or acquiring the small ones. In our case, we are mostly, but not exclusively, working with large OEMs. If I may add one last note, one exception to this general case is activities ongoing on autonomous driving, for example, for trucks. We believe that autonomous driving is going to start only with commercial cars. If you ask me, they will probably come first on trucks rather than commercial cars for a number of reasons, because of the return on investment, because of the cost of transportation pool rather than comfort, if you wish. So I think that this is an interesting, let me say, starting point where I think we will be surprised to see how fast they are progressing in the ADAS development. Maybe
also because the computers, they don't watch television and fall asleep.
Yeah, most probably is part of the equation. Yes. Probably the safety part is even more important there for trucks. Yes, but that's what I believe.
And Peter, obviously the move to autonomous vehicles needs to be supported by some changes in how vehicles are architected electrically and electronically. What are you seeing there? We've talked about zonal architectures and domain architectures coming along. Do you think that sort of changes anything for how much does autonomous driving and adding an AI and a machine learning driving machine into the middle of all of this change the rest of the car and the challenges and the work that you'll be doing in the future?
It's not so much the future, actually. So we've got many autonomous driving projects already, and that started a couple of years ago with what we call the POSIX support. So many of these systems, since we have a close link to the operating system, we think of these systems as the POSIX-based systems. And there, if you look at these kind of ECUs, very often you have a mixture of some high-performance computing, and you've got, for example, Infineon RX on it as a safety controller as well. And at some point, then they communicate with each other. They communicate with the outside world, with the sensors and everything. in order to debug, to understand and optimize the whole thing in the end, you need a view on the whole thing. And in this context, what really helps are the synchronized traces from the different sources. So to see let's say the RX, the different cores on the RX, what's going on there, as well on your Linux or QNX, plus some sensor data. So this helps a lot. So in this respect, we are not too far away from Giancarlo, what you're doing there. So, yeah, but you collect like all the sensor data, and we kind of pick what's relevant for timing.
Yeah. Yep. Now, Giancarlo, we were talking as well during our discussion earlier about the need to keep these machines cool, these HPECs cool. And you explained there's a range of different cooling approaches, including some liquid cooling. So maybe you could just explain in a bit more detail how that's implemented, and how does that require changes to the vehicle to support that cooling method?
Okay, I'll try. Maybe I can use the help of slide 6. Thank you. Yes. So, well, what I'm giving you and your audience is a bit of a sneak preview of our white paper. So we will publish end of this month a white paper on ADAS and our solutions. This is one of the elements that we try to explain. So liquid cooling. Maybe some of us are familiar with liquid cooling. If you go to MediaMarkt, for example, and you see this type of gaming computers. So the principle is essentially the same. So you want to have a zero noise type of solution. You have a small space to dissipate the heat, and you have a huge power consumption going on, right? So you need to find a way to get rid of the heat. How you do that? A fan is unreliable over time, is noisy, is subject to vibration and shocks. So probably is maybe the first choice you make, but it's not going to pay off over time. Then you have hybrid solutions. So to be concrete, a hybrid solution is a solution where let's say the hottest part of the system, typically the GPU or the storage system of the drives, gets cooled down by liquid. Right, and the liquid is then cooled down with ventilation, with a standard fan. That's what we call hybrid cooling. And then it comes to the extreme situations. The extreme situations where you absolutely need to get rid of a fan. You cannot afford it for space, for vibration. Also because if you have a fan, then maybe you need to have shock absorbers. So you need to mount the equipment in a specific way to avoid those shocks, right? Then you end up with liquid cooling. And liquid cooling is normally a closed circuit cooling. If you see the picture there, you will understand that there is a thermal analysis in the background is absolutely a piece of high tech, let me say, that is developed there, that allows to use a closed circuit cooling for the GPUs which are there. And in the picture you see, you have two high-end NVIDIA GPUs which are cooled down. And in order to get rid of the heat accumulated, you have several solutions, which implies a discussion with the customer how to best do that. This could be done with a radiator already available in the car, or you can use the AC. There are different alternatives that you can use, but the condition is that you actually discuss with the customer how to best integrate it. But I would say this is the not MediaMarkt gaming PC level of cooling. This is actually a highly engineered solution dedicated for this type of applications where there is absolutely no space available.
Yeah. So
for a minute, I thought that's maybe the reason why you go for big lorries first. So you've got it like big trailer. You can filled with eyes.
I guess they can afford a little bit more space in that case. So we get rid of one of the problems, yes. But yeah.
Yeah. So Peter, I wanted to come back to you as well on your book. So I've obviously read the book in quite a lot of detail as it was being produced, and I think one of the interesting things was just the huge range of insights that it provides into the topic of timing and the challenges of analysing software and best implementing it with that respect to timing. Could you maybe just give us a couple of words about sort of the key elements of the book, who it's written for, and is it only relevant to people in automotive, or can other people working in other industries benefit from it?
Yeah, let me start with the last question first again. So there are many aspects to embedded software which are largely independent of the domain. So we use, if not the same, but very similar processes, for example. So the way that the memories, the stack, the code execution works is all the same, whether you go to medical, telecommunication, automation, defense, automotive, wherever you go, it's all the same. So the at least the basics, I think they are relevant to any domain. And this is also what I start with in the book. So the first chapters are about the basics of how does a microcontroller work. Also, how does a build environment work? How does a compiler work? A linker. How can you optimize the memory usage, for example, without knowing how the linker or locator work? You have to have that sort of knowledge. So that's why the first, let's say, 1-2 chapters, also operating systems, the first 1, 2, 3 chapters, they deal with these kind of basics, which are not totally specific to the topic of timing. And then I switch to the general introduction of some timing theory background, and very quickly talk about different timing analysis techniques. And again, since we're a provider of one of these techniques, I try to be at least to give an independent view on this topic. And so each technology gets its own section, and they all have the same structure where I explain how the technique works, what are the use cases, what are the benefits, what are also the drawbacks. And at the end of each of these sections, I have an interview actually with one expert from that technology. So I'm talking to the guys are from Absin, for example, for static code analysis, or Ralf Münzenberger for static scheduling analysis, and so forth. Then multi-core is also a topic, and then there's a whole chapter on timing optimization, where I talk about the different techniques on different levels. And just recently, I coached one Korean OEM where we actually ran really through the flow graph that's present in the book, what to do when you face a timing problem or overload scenario, what are the steps that you can address. And so far we've been quite successful. So it's ongoing, but that's the kind of thing we're doing there. And I round off the book with a chapter on AUTOSAR and also on safety, where I talk about also legal aspects and risk in general, because there's no such thing as a bug-free software. Yes. So it's always a question about probability and risks. Yeah,
exactly. Super. Well, thanks for that overview. Just a last question to both of you. Giancarlo first. Do you exhibit around the world at various trade fairs, and is there an opportunity to sort of see your hardware in action if you're not actually actively developing an autonomous vehicle?
Absolutely, yes. So we will not have a test car available at the booth, but we will be in March at the Embedded World. That's the first chance to meet us in person and to talk a bit deeper about our solutions. And on our website, and on our LinkedIn channel, we will definitely communicate all the next opportunities to meet in person. So looking forward to meet you there.
And Peter, what about yourself? Are you an Embedded World fan?
Yes, absolutely. So we'll be there in Nuremberg and later during the year in Shanghai, China. So yes, let's meet at Embedded World.
Yeah. So I'll be there as well, of course, reporting for Elektor. Excellent. And with any luck, I'll have a chance to drop by the stand and actually see some of these things in action and meet the rest of your teams as well.
Please do so. Yeah.
Super. Well, thank you ever so much for your time. I'm just going to wrap up the end of the show now. So I'll say thank you to you both just before I take you out of the live stream. Thanks very much.
Thank you very much, Stuart. Thank you. Ciao.
Ciao. So much of the hype surrounding self-driving cars turned out to be just that, hype. But it has set events in motion that will lead to autonomous vehicles, just not in the timeframes some people have suggested. Engineers like those at Eurotech have grasped the challenge with both hands, providing highly optimized computing systems that not only train exceptionally complex deep learning algorithms, they do this under the extreme conditions of the automotive environment. And as we've seen, vehicle networks and system architectures are adapting in order to support this pending capability. However, the basics still remain, meaning the timing challenges Gliwa helped to resolve will still be there for years to come. Thanks to my experts today, Giancarlo Cutrignelli of Eurotech and Peter Gliwa of Gliwa Embedded Systems. You've both delivered us with some outstanding engineering insights. So that wraps it up for today. If you'd like more of the same, we're broadcasting even 2 episodes of Engineering Insights every month in 2023. And to keep you abreast of industry trends this year, take a look at our News Bites show, a monthly 15-minute programme on Elektor TV industry. Please like and subscribe on YouTube and share our videos on whatever platforms you use, or drop by the website at elektormagazine.com/EEI to see the topics for future shows. Finally, if you'd like to join me as a guest, write me an email, drop me a tweet, or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining, stay in touch, and don't forget to keep asking your engineering questions.